Just like with mirrors, we can derive an equation that relates the image distance to the object distance and the focal length of a thin lens. We take a couple of the rays we drew in our ray diagram to relate the image to the object. D sub O represents the object distance, while D sub I represents the image distance. H sub I is the image height, and H sub O is the object height. Using these dimensions, we can draw two right triangles that are similar because of the two touching angles. So the ratio of the image height to the object height is equal to the ratio of the difference between the image distance and the focal length to the focal length. We can take those two equations and combine them so that the ratio of the image distance to the object distance is equal to the ratio of the difference between the image distance and the focal length to the focal length. From here, we can divide everything by the image distance and end up what is known as the thin lens equation. So the inverse of the object distance plus the inverse of the image distance is equal to the inverse of the focal length. You might notice that this is the same as the mirror equation. Another thing to take note of is that for an object at infinity, the inverse of the object distance would be 0. So the image distance would be the focal length of the lens. For a diverging lens, we use the same principle, but because the image is formed on the other side of the lens, we have to change some things in our equation. In this case, the ratio of the image height to the object height is equal to the ratio of the focal length minus the image distance to the focal length. And if we combine these two equations, we get a slightly different lens equation. Sort of. Really, it is the same equation, we just make the focal length and the image distance negative because the image is on the same side as the object. So the thin lens equation can be used in all situations if the right sign conventions are followed. The focal length of a converging lens is positive, but negative for a diverging lens. The object distance for a lens is positive if the object is on the same side of the lens that the light is coming from. Now, this is always true for real objects, but when lenses are used in combination, this can change a little bit. The image distance is positive if the image is formed on the opposite side of the lens from where the light is coming from. If the image forms on the same side as the light, then the image distance is negative. Another way to think of this is the image distance is negative for virtual images, but positive for real images. And then the image height is positive if the image forms upright, and negative if the image forms upside down. Just like with a mirror, the magnification of a lens is the ratio of the image height to the object height, and the negative ratio of the image distance to the object distance. From the sign conventions just defined, we find that the power of a converging lens in diopters is positive. Converging lenses can produce real inverted images or virtual upright images depending on where the object is located. The power of a diverging lens is negative, so a diverging lens will always produce an upright virtual image no matter where the object is located.